Okay, good morning. Sorry about the technical glitch. It's always happening here. I don't know for some reason. Okay, today's lecture is, we are almost coming towards the end of we are nearly there, end of the module. So today's lecture is more about biomass and storage. So as you can see from this diagram, and before, it's all solar, right? So my job is more propagate about solar. So it's about solar, sun, and then it's photosynthesis and getting light from, then hitting the greenery, get the carbon dioxide stored in the green pockets, the photosynthesis, and then goes into the inorganic materials that is in the trunks and gets to the water and release carbon dioxide again. So that's the simple conversion. So by the end of this class, you will realize why we need this and what we can do, what we can get, and what is the importance of hydrogen and the conversion, what we get. So that's, I would presume that you should be knowing that. So that's the idea. Okay, remember to turn off your phone, please. That would be great. And before I go any further, any questions or comments you have? No, I didn't too long. Any questions? I can take a few questions before I start. No? Okay, that's fine. Okay, so that's the menu for today regarding the biomass. So I would be covering on biomass introduction, what is biomass, and conversion, biomass resources and protection, biomass to electricity, biomass to biofuels to hydrogen, and then current trends in biomass. Is that okay? Yeah. All right, okay. So how many of you know what is biomass? So, yeah, what is it? Yeah.
Rubbish, manure, waste, slaughtering and stuff like that. It's a fuel.
Mm-hmm. What type of fuel?
What type of fuel? Ethanol.
Ethanol?
Yeah. Methane.
Ethanol and?
Methane.
Methane?
Yeah.
Methane is a gas, right? Yeah, okay. Gaseous fuel. Then?
And then use that fuel then to drive it. So basically in Sweden we use biomass to create gas. Biofuel for our buses. So all the buses coming off biomass fuels.
To hybrid buses, yeah. Yeah, hybrid buses, that's good. So I know that, I know you guys are thinking it will become definitely ethanol. Obviously Guinness is there, right? So we use ethanol as well. I know. Any other different answers?
Biodiesel as well.
Biodiesel?
Mm-hmm. So it's easier because you use a lot of energy to separate the ethanol and water.
Mm-hmm.
Some people want to buy ethanol. Whereas it's slightly easier with biodiesel. Biomass can be anything really is in food.
Food, yeah.
Any going in business for food or for construction like wood, you can actually use for biomass.
Very good. Yeah, yeah. So can we use the grasses?
Yes.
Straws?
Yeah.
Not even the carbon.
Carbon, yeah.
Once it's dry enough.
Right. Yeah. Once it's dry enough, yeah, that's true.
Big problem with biomass, like it's,
Mm-hmm.
it's mostly water in this when you start out.
So it's suitable for Ireland, biomass.
Yes,
Why?
because with all the best climates, there's rain so much.
Mm-hmm.
Because the energy factor of water from so much, so there's less time for growing trees.
Sure. So you can get a lot of plenty of food as well.
Yes.
Yeah. So, all right, okay. So, but why Ireland is not waking up in that as well?
Not really gushing. Something like 3% forestry.
Sorry?
Because it's like 3% forest cover.
Yeah.
And one of the lowest in Europe, we've got, so there's also, forestry above 1,500 feet. Good chance of forestry. that. It's also the time it takes to harvest the renewables. There's no payback in the first 2 or 3 years.
Yeah, that's fine. But see, and I don't know whether how many of you are catching up the news yesterday, the New York Times news. Did you know about the China in one of the city? I forgot the city name. They closed the airport for a week. Do you know that?
China.
In China, because of the air pollution. Because of the air pollution, they closed because it's completely polluted. So, if we are not waking up now, I mean, it's already late, then we will be lagging up in the type of problem. It's not far. We have to consider for our descendants as well, right? So, that would be a huge problem.
They were
So-
the same problem with the Olympics in China.
Yeah, exactly the same city I'm talking about.
Los Angeles, they were back in the 80s, they had the same problem.
Yeah, but we need to wake up high time. It's high time. Each and every country will affect the other country as well. Other country will slowly spread. So all the combination of energies, when you consider the assignments, that is why in the guidelines we have given that you have to benchmark Ireland with respect to the international scenario. So those things can carry a huge weightage in your assignments. Okay? Right? Rainwater also takes a huge care. If there is a change in project, then you dock the points as well. All right, okay. That's what bioenergy is, right? Do you agree? That's what bioenergy is. Feedstocks, forest residues, black liquor. So you all know what is black liquor, right? So silver residues, grades. So grades is corn, soybean, grape seeds. So urban wastes, wood, cooking grease, crops. It's all the biocycle, right? You can start from the sun and you release plenty of carbon dioxide, goes back, and then get harvested in the trees, and then you release back. So it's a cycle. So it can be used for heating, power, fuels like ethanol, biodiesel, and then everyone boiled down to hydrogen. So I would be covering this cycle. I'm paying more attention to this cycle. Okay. So my entire class will be based on this in different form. Okay. Does anyone is doing I heard that somebody is doing biomass project. I forgot who it is. The guy is not here today maybe. Anyone doing biomass? So I saw few. I saw plenty on wind. Plenty of people are doing on wind. Understandable. So few are solar and somebody on efficient energy systems. So yeah, there are quite a few good projects out there as well. Right. So introduction. Is biomass renewable?
Yeah.
Why? Why it's renewable?
You can regrow it, can't
Sorry?
you? You can regrow, we can reproduce trees, we can reproduce plants, and reproduce animals.
Okay.
It just takes time.
Right, okay. If oil is reproducible. Oil.
Is it renewable?
Is oil is renewable.
Yeah, but it's going to take millions of years to get back. Time period is much that, right?
But is it renewable? That's what the question is.
We usually about 15,000 years a year.
15,000?
It's about 15,000 years to deploy every year.
It's not sustainable.
It's
It's not sustainable.
not currently.
How do you define? How do you define sustainable and non-sustainable? This is a very important question.
Depends on our consumption levels of oils. The actual levels available there are not sustainable for our use.
Mm-hmm.
You know, so we define, I would say by our use as well as the levels that are out there.
Productivity has to be bigger than consumption.
Bigger than the consumption. Any other thoughts?
It's in a cycle.
What's the second?
Most of the elements of the material in bioenergy biomass will go back through again.
Yeah, it's from the previous cycle. Yeah,
You're breathing the ashes as well. You're breathing the ashes and fertilizer, things like that. So you don't need to continuously find inputs from outside. It's a cycle.
Mm-hmm. So it's not the case with oil, is it?
No, because it's basically moving it out of the ground, that's it.
So it's spoiling the atmosphere by CO2.
Yeah, the CO2 that's released from the oil goes into the atmosphere, but the CO2 biomass it's releasing ventilation surface.
Okay.
So you're not, the net balance is zero.
That's what I want actually. So you need to have a balance. That balance should be zero, right? What Declan? Nothing. So, yeah, this is an important question regarding how do you compare renewable with non-renewable energies. Okay, and you need to hit a really key points. What is the net energy balance in this case? In these cases. So, yeah, biomass is renewable, and is it economical? Connected to farming, is it economical?
Oh yeah.
Fine.
It depends, it's what most people in poor countries actually used to do. Because of oil free. It's very economical in certain countries under certain risk oil. But it's once you have access to the amount and small amounts which are freely available. It's when you start trying to boost production by adding more inputs.
Yeah, sure.
That's when the economics get more complicated.
So as we start using more computers, more technology, then it goes down, right? It goes down. So it's all again, as I mentioned, we are all just reinventing the wheel. That's it. From the beginning, I'm telling you the same thing. So the biomass is people started using the olden days, the woods to burn things, right? To get energy out of it. So we are going to use it again. We are again waking up. So how we can invent, innovate, and smarter way of harvesting and storage. So that's all that's connected to farming and economics. Okay, multi-use, we all know what is multi-use: food, shelter, energy, and materials. We use the biomass part. Environmental concerns. Environmental concerns include land and water use, fertilizer, and other nutrient requirements. Do you agree? Environmental concerns, is it a concern? Include land, water use. I'm hitting, right from the first day I was telling the European and entire world agenda is there are three sectors, key sectors in science and technology, science, engineering and technologies: energy, healthcare and water. Right? So these are all going to be a huge challenge in the coming decade and the next decade, and also at least for 3 decades. It will be a huge challenge. So this will also be challenging. Environmental concerns include land, water, yes, fertilizer and other nutrient requirements. Right? So pinch in with, do you think anything different apart from this? Water is a huge problem going to come, right? We are facing already. And a bottle of water is expensive than Coke. So, what? Sorry?
So it's more expensive than petrol.
Yeah.
Can't believe that.
So, I'm still surprised that it's not taxing for the water. You don't have water tax, that's good.
It's coming very long.
Sorry?
It's coming in the next year or two.
Sorry?
It's coming in the next year or two.
Yeah, it was there for a long time. The next year. Yeah.
Well, let's not get started on that.
Anyway, so water is going to be other nutrient requirements. So I will be briefly touching that. Naturally diffuse and distributed, harvesting and transport and distribution are very, very important. So how we are going to harvest, how we are going to transport, are you going to transport through the grid, or are you going to store the energy in the batteries? So there are lots of other challenges. How we are going to do the challenge. Any thoughts how we can store and transport?
You can treat it like fossil fuel.
Sorry?
You can treat it like fossil fuel.
Mm-hmm.
So the big match of fossil fuel is it's stored for a long period. So biomass, you harvest it, you go to places where you harvest it once a year
Mm-hmm.
and then use it as storage.
Can you be a bit more specific?
Okay, if you harvest biomass once a year, you basically have to have a year's supply of storage for use when you So you reuse existing.
Is it in the form of a gaseous form or a liquid form or what type of
No,
form?
just as the solid fuel.
A solid fuel.
Yeah, the reason it's easier to store that way. You need expression containers only use some words.
No, you're talking about the smaller scale. I'm talking about the bigger scale.
Oh, that would be large scale.
Large scale. How you're going to do it in the large scale and then how you do it in the large scale transmission.
Okay, at the moment, if you look at how coal is stored, there was a driven miner strike in the UK and some of the 18 months coal stored before the strike started.
Sure.
Biomass, you could have maybe similar things as well.
Similar to that,
So
yeah.
you can have more storage in the top than you can in hydro, if you do it right. But yeah, transporting that and converting it, you're down to the efficiencies of it.
Yeah.
Because you lose every time it works.
Yeah, that's why it should be like a combination of solar and biomass. You can also use solar concentrator while you do the transportation and also do the biomass. So there could be several opportunities in engineering aspects as well. Okay, diffuse distribution, harvesting, transport, distribution are very important. Okay, back to introduction. So energy derived from sustainable materials, cellular matter from living or recently dead organisms. So wood, straw, waste, particles, and materials can be converted directly to produce heat and power. So it's not and power, it's heat and power. Materials can be converted into biofuels, biodiesel, and charcoal. So that's what we have discussed, almost everything. Right. All Earth's living matter is called its biomass, right? So everything is biomass, including us. So biomass is only a small portion of Earth's mass, but in human terms, it's an important energy source. It's a very, very important energy source, biomass. Biomass is constantly being replenished by the flow of energy from the sun through the process called photosynthesis. We touched photosynthesis in our introduction chapter, right? The first chapter. Okay. It's all photosynthesis. Okay, so we get, as I mentioned to you before, biomass is another form of solar energy. So, what are all the other forms of solar energies which we have discussed so far?
Solar itself,
Wind,
wind,
rain, yeah, rainwater. Later results in the again, rainwater, and hydro. So you guys now tend to agree everything is solar, right? More or less, exactly. Biomass is also belong to the same family of solar. Okay, the solar energy is captured by our photosynthesis. So as you can see from the diagram, so you hit, solar energy is captured by photosynthesis as a carbon dioxide, is incorporated as a fixed carbon. So carbon is a very, very important material for different purposes. So carbon during the growth stage of all biomass. So you have a sunlight, so CO2 goes there and stored in the leaves and the trunks, and then then it's released as a function of time or heat. Then it released, and then you convert that as a useful energy. So that's a brief description of the solar cells, of the photosynthesis. So biomass capture efficiency is about less than 1%. Okay, whereas thin film photovoltaic is approximately 10%. So we are still a long way, but if you see as we mentioned about the cost, the balance, economical balance, so biomass is better when compared to thin film photovoltaic. So we'll get back to that in the later stage, when we discuss about the current trends and the future markets. So this is a reaction, CO2 and the water and the moisture get absorbed. So we have moisture in the air, shine light on it, so oxygen, we break the bonds and form oxygen, and then CH2O as an intermediate states, and you have to produce again water. So that's what the chemical reaction for the photosynthesis. What are the types of biomass? Manure,
sewage, wood, grain,
what is it? Grain, seed, everything, okay? So, wood, right? Garbage. Garbage, right? It's a biomass. Crops. Landfill gas. Alcohol fuels. So you know what Ireland is. So that's what it is. Okay, so we have wood, garbage, crops, landfill, gas, and alcohol fuels. So those are all the different types of biomass available.
The other one was waste from slaughter.
Sorry?
Slaughter waste.
Yeah,
Slaughter was like something like 400 billion tons.
that's true.
Slaughter waste. And there's 500 billion, sorry, 500 billion tons slaughter waste.
That's right.
There's a place in the US processing turkey waste.
Oh, right.
It's shocked into biofuel, and they had to close down because they found the cost of the waste went up with 20 uses for it.
So the recycling has been done a lot, yeah.
Oh yeah, they're repercussion.
That's right. So they may not encourage the boxing meal, right? It's pretty 6th of December, but more turkey is produced. Okay. So biomass resources, energy crops, wood, agricultural crops, waste products, wooden residues, temperature crop waste, tropical crop waste, animal waste, municipal solid wastes, and commercial and industrial waste. So quite a few resources are available. Right, a few different categories of resources available, and which could be used in different types, either directly or indirectly for the biomass requirements. So the carbon cycle, I would call this as a carbon cycle. So you start with a corn, and you know how alcohol is produced, right? Anyway, everyone would be knowing. If you go to Just Guinness, you know what is happening. So you have a corn, so you finally grind the corn, and then separate it, get the sugar out of that, and separate it into their different sugar, burn it, distill it, you get ethanol. Right? So don't drink it. So you have to process this, don't drink it. Forget us. So put it as a fuel, burn it again with your car and whatever it is, your vehicle, and then CO2 which releases, and then it goes into the forest or whatever it is in the. So again, it's a reverse process. So it's an economical way of doing it, and only thing is that we are taking more of natural resources. So that's it. So this is what a carbon cycle is. So ethanol. How many of you know about fuel cells? Only one. No. Okay. Whenever I want to do something on the board, I found there is no problem.
I've seen one on the web is Envy Bike. I've
Yeah.
seen that. Someone's developed a hydrogen fuel cell, and they wanted something to put into it. So they developed this, it's like a motorbike.
So there are fuel cell bikes are there. Paul, you said you know something about fuel cell. What is it?
It's the exact opposite of electrolysis. In that the simplest form is exactly it's a hydrogen fuel cell, but it's like a slightly car battery, you have liquid inside it, electrolyte plates, and membrane, and you're pushing hydrogen gas on one side, oxygen gas on the other side, and the two are chemically reacting, and using electrodes to extract the voltage of electrons as the chemical reaction happens.
Okay.
So
I agree the argument. Okay, I agree.
It's like having a battery, except the chemicals that react.
Then why ethanol is there?
Stored.
Why ethanol?
Now you can also make fuel cells out of not just hydrogen, you can also make them out of methanol as well.
Yeah, ethanol. Yeah, can we solve?
You get thin film forms bacteria, and they can actually turn most biomasses that the bacteria can digest into.
Okay, there are two types of cells. Okay, there are two types of fuel cells. Because I just want to know why we are using ethanol. Ethanol can be used directly, and ethanol can be used as a fuel cell as well. Okay, so I have a jar of ethanol. ETOH means ethyl alcohol. That's ethanol, okay? So what I am going to do is, so it is C2H5OH, so there's more hydrogen in it than carbon, okay? So I bubble the ethanol. So what you have is, you form an electrode on both sides. So you need, suppose if you want to activate any reactions, you need to have a catalyst. So you feed ethanol directly here. Either you have some platinum or carbon. So ethanol goes in and then gets absorbed here, and then it's reduced. So it's oxidized. Proton is getting transferred. So H plus is transferred here, and then goes there, as Paul said rightly, either you can pass oxygen or air on the other side of the electrode, and then this hydrogen proton goes there, get reduced with O minus and forms H2O, water product. So during this reaction, the transformation goes from here to here, you take the current. Okay? That's what it is happening here. So the process looks like pretty much like this. This is why ethyl alcohol is there, fuel cell. So this is a typical assembly for a fuel cell. So this can be directly put into your car, and then you can feed ethanol in it. So that's another way of using it. Okay.
The big thing there is that you bypass the Carnot cycle.
Sorry.
You bypass the Carnot cycle.
Carnot cycle, exactly.
So you're getting maybe twice the efficiency, or when you've got the engines up to 100.
So the efficiency goes much higher, much higher. The problem is, again, the cost goes higher because of this. Because it uses different types of membranes and different materials as a catalyst, so the cost goes up. Okay, so there are plenty of R&D has been going for many decades, many decades, about 3-4 decades. People are still working on this. It started in 1970s. Sorry? Yeah, 1960s or 70s. Yeah. All right. So the production. So as I said, the resource, we covered research. We did what is biomass. So now we see what is production. How do you production pathways for liquid fuels. So right from the bottom from the left, if you see LPG, petrol, diesel, and they are used as a blending and refining, you get crude oil, right? If you blend, refine, and then similarly natural gas and the coal. So if you look at the other side on the right, where methanol mixed with this thing, you synthesize this, and then you undergo gasification, and you have really some cellulose and like lignin or some other cellulose gets absorbed, and that is called second generation biomass. And you can also use ethanol, butanol, biodiesels, and you can do different process of refining, pyrolysis, hydrolysis, fermentation. So all these new keywords which you can find, and then get sugar and then ferment it and get ethanol out of it. Similarly, oil crops, it's all boils down to the ethanol and biodiesel, right? So if you go from bottom to top. So you do hydrolysis, you do fermentation, you do gasification. So so in this class, this is a huge picture talking about several fuels made starting from biomass. So there are plenty of happening in this slide. So there is a reason why we put the thing in the black. Okay. So what are all the key parameters for bioelectricity production from biomass from this graph? What do you think? What are all the key steps? I would say steps. What are the key steps? Or different types? Okay, let's say different types for the energy conversion, biomass conversion. What is the key steps here in these cases?
I'm not sure you're turning the fuel into a liquid or
No, you pick the keywords from there. Pick the keywords from there. What are all the keywords which you think is involved in that biomass conversion? Show loud.
Like
Hydrolysis, pyrolysis, then gasification.
And they're all based on large molecules like small molecules.
Yeah. So hydrolysis, pyrolysis, gasification, and more. Fermentation. Am I missing anything here? Any idea? I'm missing something. Am I? Somebody was mentioning about cells, close fitting like bacteria, virus, or something. Bacteria in storage. No? Okay, I think I heard something maybe. Yeah. Okay, so hydrolysis, pyrolysis, gasification, and fermentation, is it? Okay, I'll show you in the next slide what it is. So biomass energy conversion is, you are exactly right, it's combustion, anaerobic digestion. That's the problem with Apple, you know. Conversion of Apple to Mac. So 1, 2, 3. That's not the way I put 1, 2, 3, 4. Okay. So conversion, anaerobic digestion, gasification, and pyrolysis. So these are all like 4 key steps, 4 different ways which we can convert biomass into energy. Agree? So this is not 3, 1, 1. Okay. So there's another important concept before I start talking more about conversion and the other 4 steps. So the important concept is air to fuel ratio. It's called AFR. So it's nothing but amount of oxygen that is supplied to the stoichiometric amount that is used for combustion. It's for the burning. Okay. So how much amount of oxygen? It's like pretty much like your what? Capacity factor, right? Pretty much like capacity factor. So amount of oxygen, it's a ratio. So this is under, that is called AFR, and fuel to air ratio is fuel to oxidizer ratio to the stoichiometric fuel to oxide ratio. So it's all become to stoichiometry, as Paul suggested few minutes back. It's all boiled down to breaking down of big molecules to small molecules. Okay, that is what stoichiometry means. Big molecules to small molecules in a different stoichiometry. Okay, so that's why I said at stoichiometric conditions, the combustions and the AFR and FAR are defined to be 1. At stoichiometric conditions, it hardly happens. Okay, the term equivalence is called ER, is used for both. That is equivalence ratio, if it is 1. Okay? Combustion. In case of combustion, air-fuel ratio is actual air-fuel ratio by actual air-fuel ratio to stoichiometric combustion is 1 minus infinity. You can do whatever you like, whatever you combust, depending on what type of material, what type of gas you produce, what type of chemical compound you produce. So that's why. So biomass, example wood chip, can be burned to provide process and or space heating. So we know that. Okay, the combustion of biomass can also be used to raise steam to drive engines. We know that happened before, steam engines, and turbines which are coupled to generators producing electricity. Right? So combustion. So combustion is nothing but complete oxidation of fuel. You are completely oxidizing it. Pretty much like this. This is also a combustion, I can say this, because you are going to heat the surface here. So you have a ethanol, or say instead of ethanol I have a wood passing through this, heating the surface, generating the energy, passing the oxidation. This is when oxidation takes place. That's what precisely happening. A complete oxidation. If I can completely oxidize this, then what I am doing effectively is all these organic molecules, right? These are all wood and crops. It's all organic, right? So these organic molecules have what in common? Carbon. Another thing? You're right, carbon. Another thing, another key theme. Hydrogen, exactly. So these all having carbon, hydrogen and carbon. Okay, and hydrogen is going to be a very, very, very critical key factor in determining the future energy conversion, at least definitely for future decades. So because we have hydrogen is storage, transmission is the key factors, and how it is going to be produced. So if you see that is methane, CH4O 1.5 above. So stoichiometric global reaction plus heat. So when you start heating it, hydrogen is also evolving. This hydrogen can be stored in fusion or fission reactions, anything you want. Okay. So the global reaction rate is that one, and hot gases used for heating. We know that direct heating, the fireplace we have been using traditionally, and water in central heating systems, boilers, and process conditions. Those are all the key factors. What are the process conditions and boilers and water in central heating systems? So I will go to cost analysis later at some stage. What is happening in the reactions? So you have coal. So you pyrolyze the coal, pyrolyze heating at different stage. So you throw out all the volatiles. You have a char. This is nothing but a combination of oxygen, water, and CO2, and release H2. From this, you heat further, you release H2 and CO, and partially oxidized and heterogeneous, you get ash. Right? That's typical combustion reaction. So the homogeneous, this is completely homogeneous reactions where oxidation of volatiles and light gases takes place. Heterogeneous reactions are the oxidation of char. So you oxidize it and then you get CO2 and heat. Okay? So burning of matchstick. So this is what is happening. This is another typical process of combustion. So where you undergo the pyrolysis, hydrocarbon tar you produce, and then that is oil and vapors to crack the hydrocarbons, and you have gases from the soot. So you know the soot is coming out of when you close. So that is again a combustion reaction. That is a combustion of wood and gas. That is combustion of food. So this is an equivalent thing of what you do in your fireplace, right? So I want to throw a very simple example with the matchstick so people can easily remember. So in this case, the series of processes take place from pyrolysis of food to hydrocarbons to tar, and then the gases are coming, which is luminous. Since it is luminescent, it's very important. This is luminous gas. Okay, you can see from here. I don't have a marker. So there are different. It's pretty much like I don't know how many of people have seen argon gas, argon plasma. So this is pretty much like a plasma coming out of the oxidation. Okay, so there is because of its luminescent. Okay, the ions are luminescent. Okay, and then combustion of gas and tar, and then other products are coming out and diffusion into plume. Okay, so that's pretty much is happening. The image on the center is pretty much scaled to the flame. Okay, so that's a typical combustion process. Okay, next, anaerobic digestion. So the process of anaerobic digestion, AD, involves the breaking down. AD involves breakdown of organic waste by bacteria. I think you mentioned a few minutes back, I don't know. So the process of anaerobic digestion involves breaking down of organic waste by bacteria in an oxygen-free environment. That's what our anaerobic digestion. The products of this process are biogas and agricultural fertilizers. Both are rich in nitrogen, phosphorus, and potassium. So biomass, example animal manure, can be transferred to biogas by burning. Okay, so biogas by anaerobic digestion as well, and the biogas can be used to fuel a gas engine or a gas turbine. We all know that, and or burned into a boiler to provide heat or to raise steam. Biogas is a combustible gas composed primarily of methane and CO2. Okay? So the components are the wet biomass, example sludge, manure, green waste. Biomass gas is, we know there's biogas, methane and CO2 and digestate. Very long residence time. What is residence time? How long it takes to go through the process? Okay. Any other comments? Months, days, but you can activate it by different routes. I forgot it. It's like you can use different routes to increase the residence time. So the residence time is the duration from one reaction to another reaction. How long it takes place. That is what residence time is. Okay. So that is a really very long residence time in different processing. And then variable gas production, so different gases can come out of that. Main application in gas engines and small scale. So you have a slurry or a manure, you take from the manure from the cow dung itself, you can even take a cow dung, where a lot of cattle are here, or even the food or the organic waste, which is released by the horse maybe, and then the crops. So these can be converted into, you take extract the bacteria out of it, get into the anaerobic digester and get the biogas out of that, and then biomethane, and start storing the biomethane there, and generate power out of that. So that's a very simple cartoon picture, but it tells more. So biomass with about C6 sugar beet, sugar cane, corn. The conversion of glucose into ethanol and CO2 is also a biomass reactions. Okay, the conversion of glucose to ethanol and then carbon dioxide. The optimum condition for enzymatic activity. Okay, main applications are pure E100, that is ethanol, or as a blending component for road transport or ICEs. So we can use those kind of biomass gases and ethanol for transportation and also for ICE. Okay, so the gasification ratio, the next process is gasification. So for gasification, the air to fuel ratio is about 0.2 to 0.5, and gasification is nothing but it's a chemical process by which the gaseous fuel is produced from the solid fuel. Okay, so for example, carbon with hydrogen gives CO, and then CO2, and then again CO2 plus C gives 2CO. It's a simple reaction. Usually the raw materials for gasification are house waste or compost are heated to high temperature, more than about 700 degrees, with a controlled atmosphere of oxygen and or steam. The process begins with the release of volatiles from the heated solid and leaving the char. So these components undergo the reactions with steam. Again, so can you give me an example? These process undergoes reactions with steam and oxygen to produce syngas and or a producer gas. Mainly CO and hydrogen, but includes a trace of gases. So this is a cartoon picture of the biomass reactions. Okay, but do you have any specific examples for gasification?
During the Second World War, people were in cars and turf.
Mm-hmm.
You had boilers basically, and a jet burner, very simplistically, you were spraying steam, spraying water on it, and you get a watershed reaction, and then use night gas directly to the engine.
Perfect, yeah.
And the people said we were burning tractors as well.
Yeah, because it is black light, yeah. It's true.
And the big one with that gas is two drugs. One is the cohesion value because of carbon dioxide in it.
Carbon monoxide.
Sorry, carbon dioxide.
Yeah.
The other big one is that carbon monoxide is kind of poisonous.
Carbon monoxide.
Extremely poisonous.
Yeah. So that is a huge issue. Carbon monoxide is extremely poisonous, not carbon dioxide, carbon monoxide. So
it's very hard to separate out. There's two gases at the end are hydrogen and carbon monoxide.
yeah,
They both have roughly the same heating value.
calorific value.
But they're very hard to separate from each other because you can't really equalize them, pressurize them.
Yeah, that's a challenge. That's exactly the challenge, gasification. Okay, so it's a bit of a cartoon picture. So you extract the ash, you have an so you pass the biomass, it undergoes for the water boiler, it undergoes the drying zone, pyrolysis zone, so where you evaporate it with the volatile vapors coming out of it, and then you reduce it by exactly what you were mentioning. It's CO2 plus C, your reduction. So carbon monoxide plus heat is reduced, and it goes further to oxidation zone, carbon combustion. So you have to go for crack it. So it again gives more energy as well. You need to put more heat, crack it, and then the ash protects the grate from high temperature. So you ash it. Okay. So in this process, the gases will be released after all these process, and then like extract gas and then get the gas for the combustion and non-combustion reactions with water vapor, nitrogen and CO2. So this is a typical picture, cartoon picture for the gasification process. And is it pyrolysis is the final one? Yeah. So pyrolysis. Sorry?
You get the reactions, the motion reactions, so on the higher up the chain. Pyrolysis will be down at the bottom very, very.
No. I'm talking about the fourth process in the slide. No. And see, I put conversion, gasification, anaerobic digestion and pyrolysis. So that's what I meant. Okay. So breaking down of a material by heat, devolatilization in absence of oxidants, temperature range between 250 to 600 degrees. So pyrolysis can be segregated into two processes: slow pyrolysis, torrefactions, that's about 250 to 300 degrees, biomass and heated, the charcoal and gas is produced, and energy yield of solid products. You get an energy yield of solid fuel. Solid product is optimized. Fast pyrolysis, it's like again a rapid thermal heating or rapid thermal annealing. So where you immediately heat up to 450 to 600 degrees, high heating rate. The rate is faster. So biomass heat and then char and you get bio oil and gases. So liquid yield is optimized. So where the slow is solid yield and the fast pyrolysis is liquid yield. So this pyrolysis process is an endothermic reaction. Okay. Okay, so this is what is exactly happening when Paul we were discussing about the residence time. Okay, so this is what is in case of flash heating. Flash heating was rapid heating. We heat it immediately, rapid thermal annealing, right? So if you start heating it, you can see the residence time is less. The fast heating, so you use about 10 power 6 watt per square centimeter, and also 10 power 5. So whereas the slow heating, you can see the different process, whereas charcoal and then you get tar and then you get gas. So you tend to accumulate more gas in the flash heating, whereas in the slow heating you tend to accumulate more tar and charcoal. Okay, it's the solid fuel and then you get gas or liquid fuel in the other. Okay, the slow pyrolysis this is the picture for slow pyrolysis where different atomic of oxygen to carbon ratio, you can see that. So you start with anthracite, coal, lignite, peat. So peat is another thing which is there in Ireland where the energy is more, so it can be considered as a biomass. Peat, lignin, and then the biomass is, say for example, its torrefaction is about 250 to 300 degrees, and you can even take cellulose and other things. Okay, so example again is different menu. We can take different feed products and different products and use it in the volatile with acetic acid, methanol and other organics, and put it in the oven, recover the product, analysis and mass energy balances. So there are quite a few processes are there to get it out of the energy out of this. Okay, fast pyrolysis is again use the biomass, different temperatures, you get bio oil, and then you can also reduce it to biotar and biogas and char. So carefully controlled conditions, high heating rate is 70%, whereas that gives more higher percentage. Okay, so far we discussed about different types of biomasses. So in all the process, whether it's biomass, wind or hydro, all the process leads to hydrogen. Okay, that's what I want to convey in this slide. All the process leads to hydrogen. You have a hydrocarbon. Coal has a hydrocarbon, petrol has a hydrocarbon, natural gas has a hydrocarbon. So it's a molecules. Okay, so these molecules get transmitted. So you have a transmission systems, grids, smart grids, whatever you can take. So you burn it. The electrons are released, and along with water. So that has hydrogen. So again, if you go for water, nuclear, geothermal, hydro, wind, solar, everything. So when you break this, you get hydrogen out of that. They're either a reverse process of electrolysis. So that hydrogen could be used as a different plasma, fuel cell for transport, and even the biomass plants has a different hydrogen. So everything boils down here. It's a very, I want to capture, so you're saying that solar is the prime, hydrogen is another prime sector. So you get solar the source, hydrogen is the product, main product. So the future is going towards hydrogen because all the molecules, all the components have hydrocarbon in it, and hydrogen has a huge potential to replace the energy things for hydrogen fuel cells or solid oxide fuel cells, everything. So you can use it for transportation, home business, and other purpose. Okay, hydrogen is only an energy carrier. It is produced from the energy sources. Okay. So renewable energy leads to hydrogen. So renewable energy, so you heat it, you thermalize it, you get hydrogen out of it. For mechanical energy, electricity, and again electrolysis, you do electrolysis, you get hydrogen. Biomass, when you do the bioconversion, again the organic molecules are released, hydrogen is there, so that is also released and hydrogen is coming out. Photolysis, how many of you know photolysis? What is photolysis?
And it's breaking bonds with so much. So, when they've got fuel or not, for electrolysis, you drop the voltage by half if you use it got so much. So it means you only supply half enough energy to get the same, half of the electrical energy to get the same amount of hydrogen.
Okay. That's perfect. I agree. Thanks, Paul. So hydrogen production. So as I said, you can wind. It is producing photobiological production, photoelectrochemical water splitting. So you split water with respect to light. You use the light to split water, the high energy photons, and different types of membranes in it, and then you take hydrogen out of it. And then pyrolysis of the steam, solar assisted production like solar concentrators and solar cells could also produce hydrogen. Biological, we have water gas shift reactions that also produce hydrogen. So there are plenty of ways of producing hydrogen.
But when you say biological water gas, do you mean you use water gas reaction by electricals or biomass or
Biomass.
what's on biomass?
Okay, what are the environmental issues of biomass? Biomass still has an environmental issues, right? So land, water, and nutrient consumption, pollution from growing and harvesting. Yeah, it will be there. Effluents for thermal conversion process, combustion emissions like centralized steam, electricity generation, refuse based fuels like trace of hydrocarbons. That is again another problem, huge problem. Dioxins, furans, different types of gases coming out of it. Sometimes you fluorinated gas may come out of this if you use a different biomass. That's another problem. Trace of hydrocarbons and metals, hydrochloride, hydrochloric acid. Wooden stoves. That's another problem in wooden stoves is polymer release of polymer, PAN, complex organics, and fine particulates. Fine particulates is again causing pollution in different ways. So, and CO2 management. If fossil fuels or biomass consumption offset by new biomass growth, then you need to have a CO2 management. So these are all the challenges, not challenges, these are all the environmental issues. There are challenges are separate. So environmental and power. So there is an issues. So environmental and power is like you have a dedicated feedstock systems. So we are talking, our course is more on renewable energy technology, systems, and economics. So I just want to cover the technology bit, systems and technology bit here. Okay. So we have a dedicated feedstock supply systems. Then that is your forests or whatever you can call sustainable nutrient leaching. The erosion, biodiversity is there. Use it, produce it, store it. And then rain is again, same Clean Water Act is coming out. So national pollutant discharge, storage, ash. So this is the complete cycle. So where you can get power, store power, transfer power. So this is the picture, storage, production, storage and transmission. So current and future. So biomass currently provides around 1100 million ton of energy. That's about 50 exajoules of primary energy per year. Out of that, 190, that is about 8 exajoules per year for commercial heat or power, and 40 milliton is about 1.7 year for liquid transport fuel cells. So it's quite a lot of amount we are using it already. So traditional biomass accounts for about 800 million tau with about 35 exajoules per year. So in a blue map scenario, biomass use increase to around about 3,400 and close to about 145 exajoules per year in about 2050. That's what the predictions. Pay careful attention to this slide, okay? Okay, next slide. You need to pay careful attention. The reason is how this is a picture shows how the transformation takes place between 1700 up to 1900. Okay, what are all how the deforestation takes place and the damaging the environment. So the year will be changing 1720. Pay attention to the green areas that goes into red, where the intensive cropland changes, and you can see how the dense land will change, and tundra, hot desert, savanna islands, how all these things are changing. You can see as a function of years. So we are losing a lot of energies by usage of different technology, and also for population growth, as simple as that. That is another thing. So you can clearly see that the red regions are more intensive cropland, and where we have tropical forests has gone down a lot. All these tropical forests have gone down a lot and more, but still Africa seems to be okay. This is one of the regions which Brazil could be one of the reasons. Brazil and maybe a little bit of Australia, maybe. This I took it from another slide from from the Eindhoven University, Netherlands group. Okay? Sorry? Brazil is a pioneer in biomass. Brazil is a pioneer in biomass. Okay? And in fact, they supply a liter of oil or a liter of ethanol, biofuel for about 20 cents per liter or something. Very less. Okay? So that's yeah. So trends of biomass use in energy. So as you can see that it's growing very rapidly. Okay, it's all boiled down to what US dictates, right? 1970s oil peak came and everyone wants to go to renewable energy. So that's why the data is coming from 1970s. So from 1970s to 2009, it has grown logarithmically upwards, right? So there's a huge growth there and a huge potential to explore. And bioelectricity, out of which the electricity generation, as you can see, Brazil takes a huge chunk with respect to United States and other rest of the world. Even Germany, I'm not sure actually, I'm not sure whether that's correct. So Germany is also going for biomass as well. They are also in the table. So these are all the top 5 countries using the bioelectricity generation. And the recent trends with the biodiesel and bioethanol, as you can see, again Brazil and US produces good bioethanol futures, and also the EU is also very keen in the biodiesel rather than bioethanol. Okay, so the global biomass potential is about world primary energy supply roadmap in about 2050. We should be start using more of biofuels and bioenergies. With the roadmap vision says it's about close to about we'll get close to 10 million ton of energy from using the primary energy source of biofuels and biomass. So this is adapted from an IEA publication. So biofuel roadmap again. So the global biofuel supply grows from 2.5 exajoules to 32 exajoules in about 2050. Biofuel share in total transport fuel increases from 2%, that is today, to 27% in about 2050. So diesel, kerosene type biofuels become particularly important to decarbonize the heavy transport modes. Biofuels could reduce the global transport emission by 2.1 gigaton of carbon dioxide emission in 2050. So there are a huge challenge needs to be addressed. Large scale deployment of advanced biofuels will be a vital need to meet the roadmap targets. So as you can see that there's a huge curve going from 2010 to 2050. There is a huge different needs for biojet, biomethane, ethanol, different types of fuels, biodiesel, and ethanol conventional and then ethanol non-conventional as well. So what is the scenario in Ireland? So this is what Ireland is up to. Okay, in Ireland we use energy crops, organic fraction, landfill gas, wet organic residues, wood. So as you can see, major chunk coming from wood because we are green, shamrock, right? So major chunk comes from the thing, but there is the cap is there is an increasing demand that goes on the energy crops as well as also organic fraction. That's what the prediction in 2020. So we are not far. We are also catching up. Okay. So overall benefits and impacts. So the benefits is carbon neutral, as we know, because of the carbon dioxide goes and comes back. So carbon neutral. That's good. Can be harvested in liquid form for transportation. So we know that ethanol is coming out of that. So that's one of the examples which you can use. Large choice of biomass materials that can be matched with local climate. Sustainable energy. Yeah, it is a sustainable energy source replenished from the sun, not from some. Okay, I have to change that. From the sun. Security of supply. Waste materials can be used. So it can be reused. Where what are all the rubbish which you throw also could be reused. But byproduct of some process in fertilizers. Impacts, yes, low energy per unit area. Social impact of replacing good food producing land with energy crops. That's a challenge. Societal impact, only viable as a component of an overall energy delivery system. Okay, there are some FE emissions in CO2 emissions related to fossil fuels, but particulates of NOx, yeah. This particulates is a real challenge, particles of nitrous oxide, which will blocks the challenge. Okay, so opportunities of biomass is reducing the greenhouse gases, CO2, restoring forest resources. As you can see from the animated slide, how much forest which we have lost from going from 1700s to 1900s. So with about 200 years, how much we lost. So that's again how we are going to restore the forest. Renewable carbon source for energy, future dominated by non-carbon based electricity. Example, nuclear, geothermal, solar. Biomass become a significant raw material for liquid hydrogen fuels, chemicals, and other high value products. So you can even start thinking of making products out of biomass as well, like creams, face creams. People are starting making face creams, naturally face creams. Not started, there are plenty of people are already doing for decades. Okay, but it's not highly scaled. Okay. Sorry? Plastics, yeah, it's all. You can replace the oil. Wherever the oil goes, you can replace it. But you need to go for large scale, you need to address those challenges as well. That is the next thing. Challenges. What are the challenges? Okay. So biomass to electricity and fuels, R&D opportunities and challenges is increasing conversion energy. That is a challenge. Better catalysts, lower land and water use. Water use is very critical here. Lower land and water use impacts, harvesting and processing. Municipal and food processing residues provide opportunities for scarcity of landfills, concerns about diseases and vectors and toxins. So what are all the things that are coming out of that will be toxin as well. Environmental effects of biomass utilization warrant careful scrutiny on needs and approval with low carbon emissions approaches. Advantages, countermeasure to global climate forcing for fossil CO2. Exactly, it's a countermeasure because of the C neutral, renewable carbon source from premier products, ecosystem management like forests and water, facilitate transition to lower fossil contribution, and genetically tailored crops from sunshine to gasoline. Okay, use everything is solar, right? So use sun to gas, and economics is still a major challenge. How we are going to do at a large scale. Okay, I think I am pretty much on time. So I will take a break now, and next class we will talk about storage. Is it okay? Okay, let's start again. This is on storage. So what do you want to store? So does anyone recollect this image? Sorry? Thalacker? Yeah. That's in Ireland. Yeah, finally, yes. I'm surprised to see the two Frenchmen are not here to listen about this.
There's one right here.
Say again?
There's one in the back there.
Oh, one in the back laughing. All right, okay, my friend. Okay, that's fine. So they have a good storage system, about 290 megawatts per hour for 5 hours, with a head of about 280 meters. So it provides about load leveling, peak shaving, regulation, and black stuff. Running since 1974, quite long. So it's quite good then, right? So we are there in the race. Right. Storage. Yeah. Storage, introduction. Why we need to store energy? Why? It's a question. Why store the energy? Demand consumption versus resource and production. Energy storage systems. Mechanical, thermal, electrical, and chemical. Is there anything different you can see you want to add? Tell me why store the energy. So I think it's a stupid question if I ask you because you know everything now.
If you look at the single electric market for the island, you see that at night time on some days, the price is about 3 cents a kilowatt hour, and at peak during the 7 o'clock, it would get up to about 30 cents per kilowatt hour. So the cost of electricity depends during the day.
That's true.
And the reason why it's so expensive is you need to have plants there to do it. It used to be the case in the UK that they had one gas-powered power station that was only used after Coronation Street. Or during the break.
The break, yeah. That's true. That's true. So.
Turn on billables as well anyway. It's all they use the cheap power at night, say the pump the water, and then it's effective, you know, it is a storage solution really for the electricity. You know.
Sorry, say again?
But it's stored like the water used to pump, and there's energy required to power it.
Hydropower,
Yeah. So
which we did last class, right? It's a similar thing, yeah. Perfect, I agree, yeah. So the lesson for the day is use it before 7 o'clock to save more money. Right. So I think one bad thing I did is I put the slides up front so people can answer the questions. So what are all these energy storage systems in common? Okay, that's what I'm going to discuss today. Okay, so energy storage. So energy storage is nothing but the conversion of one energy into other energy form. So it can be used later and when required, right? So you convert one energy into another energy, store it. So say for example, I want to store hydrogen in batteries or somewhere and then release it. I store it as a chemical energy and release it as a heat energy or either way. So that's one of the examples. And then industrial energy scale storage technologies are measured in terms of their output megawatt to their capacity megawatt hour. Okay, and the most common type of energy storage is spinning reserve. Anyone have heard this term, spinning reserve? Spinning, head spinning, tail spinning, spinning reserve, where power plants operate at a level slightly below the point where they begin to produce power. So this allows them to react quickly to large swings to the demand, right? So, okay. I know that several people here are working on electronics, electronic instruments, instrumentations, and all those things. So, guys, have you come across statistical process modeling, SPC?
what about it? I go mechanical, so I come a bit of that undergrad, you know.
Mm-hmm. So my class is making you sleep now, okay? So, okay, tell me from this. So the most common type of spinning reserve is nothing but the power plants operate at slightly below the point that they begin to produce power. So they start to operate below the threshold, right? So you say, for example, if you have a Gaussian curve. You know what is a Gaussian curve, right? So, there. You're very sharp these days, so you're not sleeping now. I can run with you in a couple of minutes. So either you can take a Gaussian curve like this, or like this. Okay, either you can take a Gaussian curve or a curve like this. Okay, so if you take a Gaussian curve, so the peak power, say for example somewhere here or somewhere here, this is the, I take this as completely filled, and then this is full with half maximum, right? Okay, so what you want to do is spinning reserve is nothing but the extra generating capacity that available by increasing power. So you operate well below the peak power so that you manage the demand. I mean, we prepare you for the inevitable. So that is what spinning reserve is. So either you can operate like a threshold, below the threshold. This is where it started to rise. So you operate below threshold so that whatever happening after that you can secure it. So that's one of the things which achieved by increasing the torque. So these can be, this for most generator, the increase in power output is achieved by increasing the torque applied to the turbine. It's again more rotation, more spin, that will increase the turbine torque. Okay, comparing the storage technologies. Most important factors are cost and return on investment, right? Study. It's as simple as that. I have more money. There in the store. Either put it in the bag. Not at this stage.
On the mattress.
Put it in the bag, get some interest, 5%, 10%, return on investment, get the money back, because you're storing, right? You're storing your money in the bag. Or definitely you're not going to put it in the share market now. Okay, so put the money where it is secure and get the return on investment, right? That's exactly what energy is. You produce more energy, you want to store somewhere, right? And then release it. It's exactly like running. Then you run. You fucking hell, I'm really exhausted. I don't have any energy. So you sit there, eat, so get your energy stored, release energy again. So that is a simple process. So you need to have return on investment. So I am going to invest. I eat more, so then I run more. So I'm investing. So return on investment, efficiency, cycles. So these are all really critical, important factors, right? And influential factors, response time, from milliseconds to hours and days, energy density, size and space requirements. It's another critical factor. Environmental impact. Is it going to be toxic? Is it going to release toxic effluents? Or when processing, it is toxic. What is happening? So environmental impact is critical. And then the charge time for batteries. If you are using storage as a battery, for big industries, how long it is take to charge the batteries? Okay, I can't wait for overnight to charge the battery and put the battery in the car and go. If I'm in a hurry, go somewhere in emergency, I don't want to wait for it. So what is the charging time? What are all the influential factors? So those are all the critical factors which we need to go. Okay. Why store? Okay, that's another thing. So I mentioned about the bank and all those things just to get an information. Why store? Mismatch demand and production source. Sir? Yeah, it's up to 1 o'clock. Up to 1, yeah. 10 and 1.
Sorry, just double check.
Yeah, that's. Is that correct? 10 to 1, right?
Yeah.
Yeah. That's
Last 10 weeks.
right.
For the past 10 weeks.
You're in the past 10 weeks, but under the assumption it's 10 to 1, okay? That's fine. Okay, mismatch of demand and production. As we said, mismatch of demand and production is like morning 7 to morning peak hour demand and off peak demand. So how we are going to do that? Load leveling, transient makeup, storage allows high efficient operation for energy production. So all these four are more or less interrelated. Okay, what is load mismatch? So if I take the solar flux versus load, so solar flux versus load, you can see that it forms a similar Gaussian curve, but the load varies a lot as a function of hours. As Paul mentioned, he was slightly hitting the curve around 6 o'clock when people started waking up early. So the load goes high and then high when the ladies rest at home or they start watching TV, you watch TV. So you can see the necessary of the demand, rise in demand of the curve. So the load mismatch. Okay, seasonal mismatch. So we have a season as well, right? Between Jan to December. So again, it's from another Gaussian curve as well. If you can see, it's pretty much the same. So your flux use is more in Jan to May, right? So you can see that you use more electricity when in summer it's the other way. Solar flux is more. So we tend to use lesser, and it goes higher as well. So this is a bit of a Gaussian curve. So the trend in monthly average of solar flux electricity use for this is taken in Arizona.
There's one thing there that says the most electricity is in July.
Sorry?
Air conditioning, yeah, so it's
Air conditioning,
it's only just in Arizona there today, yeah, that makes sense.
That's in Arizona. So, okay, right. Energy storage for electricity grid. So, central plant, step up transformer. So this is a cartoon picture of the energy storage for the electricity grid. You use the central power plant, transformer, transmission lines, bulk storage, take from the renewable. Similarly, the industrial roads use smart grids and other ancillary services. For residential storage, okay, you can also use PV and then different loads and distributed storage, electric vehicle, and other distribution loads. So there are commercial loads as well. So there are plenty of things, innovations and engineering has to be done on different types of energy storages. A bit of engineering work is there as well. So I pick 10 energy storage for electricity grid, top 10 challenges or top 10 things. Smart grid is the one which entire Europe is going towards smart grids, okay? And increase the use of demand response and load aggregators, that's another thing. Rich electricity price signals, tax and regulatory incentives, transmission capacity and constraints, that's another in the top 10. Expected proliferation for electric vehicles, you know that Ireland is the green cars and all those things which we are going into, right? So that's again, 0.6 and 0.4 are tagged together, and even 0.3 as well. So increasing use of intermittent renewable energies. We know what is intermittent renewable energies are, right? So modular distributed energy resources, reducing the generation of fuel use and air emissions, and finally storage technology innovations. So these are all the top 10 electricity storage, energy storage for electric grid. You want to add anything or agree to disagree or disagree to disagree? Looks like that I have woken up everyone after the break. Some people are sleeping before that. Okay, let's move on. Okay, right. Thermodynamics, first law. First law thermodynamics, second class. We did. Okay, so all this energy is either in transition or stored. So inherent sources of storage energy. So you know that from the first law of thermodynamics, Declan, is it right?
Yep.
Huh? Don't sleep now, don't sleep.
Looks fine.
Looks fine. Are you happy? So Q, you supply heat. So heat by what? Convection, conduction, radiation. You guys remember the term? You guys remember the term? Conduction, convection. Rings your bell? Huh? Sure. Okay, conduction, convection. So you have a conduction, convection. Use that. Mechanical, electrical energy. That is energy transfer. Microscopic energy. Thermal, chemical, electrochemical, and nuclear. And then this is transferred into kinetic energy and then gravitational potential. So this is what sums up the storage, pretty much. So you burn energy, you store according to the internal energy, and then transfer it to kinetic energy, and then take it out as a gravitational pressure or electromagnetic. I'll give you an example. Okay, types of storage. Mechanical, that's potential energy, pressure, kinetic energy. Okay, so it's mechanical, right? Up of the hill, crest, with potential energy, go up, kinetic, come down. Okay, so and then it depends on the pressure. So thermal, heat energy. Chemical, can we say hydrogen? Okay, as I mentioned, you store the hydrogen somewhere, release it. Okay, electrical, batteries, ultracapacitors, supercapacitors, nonsense capacitors, what are this? Sorry, batteries could be chemical as well. Yeah, but it's more used for electrical purposes. Okay, so let's map these into first law of thermodynamics. Can you map it? Can you map it? Let's have fun, sir. Let's have fun here. How we can map it? How we can map mechanical, kinetical, and kinetic and electrical? I did the mapping here, right? Mechanical, electrical, thermal, chemical, kinetic, and potential. So let's map it this, okay? So you have molten ice, hydrogen, hydrates, metal hydrates, batteries, it's all chemical, right? So it has a stored energy, delta U. Inherent, delta U is nothing but from the first law of thermodynamics. What is delta U? What is delta U in the first law of thermodynamics?
What is the first law?
No, sorry, repeat what you said then?
I'll kill you, man. From first law of thermodynamics, what is delta U?
Oh, the change in total transition energy?
Internal energy. That's an internal energy, right? So that's delta U. Okay. Delta U plus delta EK. So it's, what is it? EK is kinetic energy. So kinetic energy is linear, rotational motion, linear motion, right? So that's a flywheel. It's a flywheel. Okay, let's map. And then delta EP, potential, gravitational. So you have compressed air, ultra caps, or pumped hydro. So what happens when you pump the hydro from potential to kinetic, right? With the transformation. So this is pretty much like storage. It's let's have a bit more relation than to the first law of thermodynamics. So what now? Mechanical. Let's see what is mechanical. So you have a pumped hydro, right? At times, the low electrical demand, excess generation of electricity is used to pump from the discharge to the reservoir, right? That's what we are pumping. Pumping from the, so the overall efficiency is about 70 to 85%. So what you do is you pump from here up to there, and then when the peak demand comes, you allow the free flow. So what is happening here is you convert the mechanical energy into electrical energy. You pump it by mechanical, get it done, right? So pumped hydro installations, I just want to give you this regarding the storage. Pumped hydro installations, you can see, Europe is about 28.4, primarily Italy, Germany, and Russia. Every year is Germany there, right? Huh? Are they rational thinkers? Yes, they are. So how we can catch up. I want to see all these key points in assignments. I'm very serious. I want to see international standards, how we are going to compare, and what needs to be done to catch up the international standards, and how Ireland can be in the top 5 or top 10 table, and what needs to be done, both in the policies, in the technologies, and also in the economics. How well balanced, if we can propose a model, that would be fantastic. Okay, with the computer simulation. Okay. So you can see that Europe is 28, and US is 27, and Japan. What a lot, okay. And rest of the world is about 7%. Australia, Iran is there. I was slightly surprised to see Iran there actually. So and China as well. Okay. So that's what it is about the pumped hydro installation, about 57 gigawatt of storage. Okay. So compressed air. So the compressed air energy storage, it is called CAES or whatever it is you can refer to the compressed air to be used later as an energy source. At utility scale, it can be stored during the periods of low energy demand, off-peak demand, and for use in meeting periods of higher energy peak load. Okay, so this is what compressed energy is. So the operation, use of peak electricity to compress air or store in the energy reservoir, underground cavern, above ground vessel. When electricity is needed, the compressed air is heated. So you compress the air here, and then you heat the air. Okay, you compress the air to the sea. You can see that there's an air in there and air out there. So you compress it here with the cavern, and then you use the pump here to compress it, and then generate it and use the turbine there. So that's what the electricity is needed. The compressed air is heated, expanded, so it undergoes adiabatic expansion and direct to the conventional turbine. Okay, so the efficiency is really greater than 70%, and sitting is limiting. And second generation, higher efficiency, faster and lower installation cost, adiabatic expansion, and little or no fuel is used. So only 2 first generation systems are operating, One in Germany, another in Alabama, since 1978 and 1991. So this is another effective way to compress the air and generate the electricity. So another storage. Okay? Flywheel. How many of you know flywheel? Steam turbines. Okay? Mechanical guy. You are a mechanical, right?
Yeah.
I need your answer. An aspiring answer from laser guy. Okay, I'll give some time for you to Google it, okay? Any other? Flywheel? No? Most cars have flywheel. Mm-hmm.
They're intestine on the going for months and months and months. The practical ones, because the weight is in, you're about 15 minutes.
Yeah, exactly.
So it's a very short time, usually just enough.
For charging.
No, yeah, they're using for, you use it long enough to get your generator going. They're using it for like a power line, they use that.
Yeah, for cars it's for you can use to charge the batteries as well. Any other strange? Flywheel.
Honestly, all I know is like cars and tractors.
Flywheel.
What they're doing is, you dig a hole and you put them down in the hole.
Yeah.
Because if the bearing breaks, something happens, the amount of energy stored is going to make it red hot or instead of flying miles.
And that's what I said. Yes.
If the bearing breaks, you end up with a hole full of red hot broken flywheel instead of basically destroying
That's
the
right.
action.
That's true. Agree. Okay, that's fine. So the basic principle is E is equal to I omega square. What is E is equal to I omega square? Half omega square. Half I omega square. Speed of? Yeah.
Angular momentum is probably a major.
Finally, he's woken up. If I put some physics, he'll be woken up. Okay, that's one. Yeah, angular momentum.
Speed of radius.
So it's a flywheel, right? The wheel is having a momentum, angular momentum that takes care.
What is the inertia?
Yeah. And he's also getting smart now. So the guy probably I should teach more physics concepts, right? Probably, huh? Okay. It's very late realization towards the end of the class. We're doing this, okay. I would love to do more physics than this. That's fine, no problem at all. Okay, let's go. So you have a hub here and composite rims. So we have magnetic bearings, motors, and then the rectifier. So it's compound of series of reactors. So it's as Paul mentioned, it works on more on the I omega square, the rotation. So you have more rotations. I think it's an instantaneous power. So you store the power with instantaneous with magnetic bearings and magnetic storage, and then you use it for bidirectional inverter and the bus into the load. Okay, the operation is it stores kinetic energy in a spinning rotor made of advanced high strength material. As I said, when it starts, it's in the material there, high strength material there. It stores and charge and discharge through a generator. So you have a generator that charging and discharging process takes place. Okay, charge by drawing electricity from the grid to increase the rotation speed. Okay. And discharge by generating the electricity at the wheels as the wheels rotate slows. That's why it is discharged. So it has charge by drawing electricity from the grid to increase the rotational speed and discharge by slowing down. Okay. The features are limitations to the energy stored. As we mentioned, it's not a long term. So it cannot store more energy. So it's limited. Primarily for power applications, it's an instantaneous power applications for anything. So high round trip efficiency, about 90%. Okay, that's another storage. Okay, thermal, sensible heat. Okay, Q is equal to MC delta T. Anything in suitable? Sorry?
Is that the capacity factor?
Capacity factor. Jesus, I'm going to die now. Or I'm going to kill this guy.
specific heat capacity.
I'm going to kill this. I am using thermal.
Heat capacity.
Yeah, specific heat capacity. We did. This has a huge meaning. Q is equal to MC delta T. Fact of life is also there. You know what is fact of life? Work, heat and heat work, whatever it is. Okay? Okay, that's what it is also there. So Q is equal to MCP delta T. So CP, specific or latent heat, phase change. Okay? So thermal energy storage tank. This is the thermal energy storage tank. Stores about 25 to 42 degrees Fahrenheit. Chilled water for building air conditioner services. Water is cooled, so you cool the water. And the mechanical chillers use low power cost, off peak or rate shifting energy. As these tanks are generally located in the campus type settings, so higher architectural aesthetic needs to be. So you can use a huge chiller to cool it, and then when you need it, you heat it up to 25 to 40 degrees, and then you take the energy out of it. Okay, chemical storage, high energy density possible, ability to use alternate energy, carrier, exclusion of hydrogen. Okay, so hydrogen production. With only minor modifications to existing and developing technologies, hydrogen can be produced efficiently and cleanly by nearly any resource. Okay, so you know from my about 10-20 slides back, I mentioned about hydrogen importance, right? So you get hydrogen from everything, from chemicals, from air, wind, everything. So how we are going to harvest it? That only needs the rational thinking and also needs some smart thinking as well. So with only minor modification to existing, this is what I mean existing, and developing technologies. There are quite a few developing technologies, hydride batteries, fuel cells, electrolysis. So how we are, okay, I'm coming back to electrolysis. Hydrogen can be produced efficiently and cleanly by from any near resource. Hydrogen made via electrolysis from excess nuclear or renewable power can be used as sustainable transport, fuel, or stored to meet peak power demand. Okay? So hydrogen made via electrolysis. What is electrolysis? Water. Break bonds from water. That's it. So it looks very easy, right? Yeah, but it's not. From excess nuclear can be used sustainable transport or stored to meet power demand. So hydrogen production again. Hydrogen produced by decarbonization of fossil fuels can enable the continued use of fossil fuels in a clean manner during the transition to the ultimate carbon-free hydrogen energy system. So hydrogen also can be decarbonized. You can also decarbonize the fossil fuels and then remove hydrogen from this using different type of catalysts so that you can get a carbon-free hydrogen as well. So biomass. So we talked about biomass a lot today. Biomass can be used to produce hydrogen and other value-added co-products such as activated carbon, fuel additives and adhesives when it thermally treated under relatively mild conditions. So this is really key for other concepts as well. How to avoid oil and go for biomass and hydrogenized products. Okay, so when we start thinking of using the thermally activated process with different stockability of hydrogen and carbon, we can make a lot of other products as well, like adhesives, fuel additives, and activated carbon could be used for catalyst for this kind of process as well here. Okay, now, so this is part of the biorefinery concepts wherein chemicals, fuels and materials are produced by biomass requires in an integrated process. Okay, an ultimate hydrogen economy vision should be there. Ultimate hydrogen economy vision features hydrogen production from sunlight, water via photoconversion. So that's what we saw photolysis, right? That's to photoconversion. Several processes including semiconductor, biological are under intense development and investigation to provide clean hydrogen for the hydrogen economy. So this is where the technology is going to go in the production, hydrogen production. Okay? And photoconversion. What is photoconversion? A system for producing hydrogen and oxygen from water. Okay? a promising option for an ecological future, ecological clean future. Okay, this is a really promising technology because there is no damaging greenhouse gas emissions involved in this, and it stores quite a lot. So you can see that this is the latest technology with the different ferrites with the nano. I just want to introduce some sort of nano here because I haven't so far introduced anything. So I want to introduce something of nano for storage. So you have a nano wires. These are all nano wires. It's dimensions of less than -9 nanometers. So 10 power minus 9 nanometers. So where your potential to store more will be there. So that's what is happening here. It's a photo conversion. You shine light and convert the energy. So where you can clearly see as a function of different percentage between the nanowire and the nanocrystalline, you can see that there's a huge change in the conversion efficiency. Okay.
How many years are we away from seeing that actually happen?
Sorry?
How many years are you away from seeing photo conversion happening on a commercial scale?
On a commercial scale, I think there are several. It depends on what type of products which we are going to go, right? So photo conversion is already existing. Yeah, it's already there in supporting for the batteries. It's already there. People started investigating that in the what do you call this? If you go for the smart chips, okay, these smart chips are like countries like Canada, right? That there's more coal. Say for example, the winter is so harsh, so for heating up, right? For heating up their cars, people have started using the photo conversion and store the energy there, and then burn it, get the energy. So these are another process that they are using in a very, very small scale, just for the car startup and them. But as you said rightly, I would say it depends on the innovation. For me, it's any transformation in innovation takes place at least a period of 10 years or 15 years, from small products to the large products. So that's what I would say. Okay, so I think most likely batteries is the final part of my storage. So batteries. So everywhere. Dell batteries, touch weight, screwed up technology, so I couldn't get it charged. So batteries, you can see from here, from the pellets to the child shoes, charging for measuring the level of citrus. You use batteries, right? For the multimeter. Batteries,
Just like it.
robo, magnet, ladybird, and giraffe. Everywhere batteries. Okay? That's what. Storage. So it's a huge multi-billion-dollar market, batteries. Innovation in batteries, storage is a multi-billion one. So I just want to give a quick, brief recipe of operations of batteries. Okay? So quickly, how it is happening. So you have an electrode, say for example, how many of you knows the operation of batteries? Oh, everyone. 1, 2, 3, 4. So only 3, minority. Minority guys, okay guys, no problem. So you have a 2 electrode, cathode and an anode. So what happens is one is oxidation takes place in the reduction, and then you measure the current over the voltmeter. Okay? Are you okay? Right. So the half cells are linked by a salt bridge. That's membrane that separates and transfers ions, but not water molecules. So there's an electrolyzer. The electrolyzer acts as a mediator there, and then deposits. Okay. So the primary batteries which can produce current immediately on assembly. Any example of primary batteries? Carbon zinc. Then zinc oxide. Zinc air. And then alkali batteries. Alkali electronic batteries. There are non-rechargeable as well. So alkali batteries are non-rechargeable. Sorry?
You can get about 14 or 15 charges out of ordinary batteries if you use a liquid AC and charge.
Like he's a dangerous guy now. He's going to burn everything. So
Just trying to do it.
Yeah. So secondary batteries are rechargeable by applying electric current, which reverse the chemical reactions that occurs during the use. So lead acid is the oldest one. Lithium ion phosphate batteries are the fastest charging and discharging batteries, next to supercapacitors. Supercapacitors is another huge area that is growing up. Okay, there are different types, and you can use even carbon for supercapacitors. Okay, so that is the technology innovations that are happening there. Okay, for storage. Lithium ion batteries. So, my God, that's why I say it's a huge market. Okay, the anode of a conventional lithium ion cell is made up of carbon. The cathode is made up of metal oxides, any metal oxides. Okay, and the electrolyte here is a lithium salt, is an inorganic solvent. So there are plenty of things that are happening on the lithium. So this is a typical lithium ion battery. You have an anode and a cathode. You have a separator, and then that's inside the battery is like they call compact devices, and then you have different reduction and oxidation mechanisms takes place when you do the reverse charging and the recycling charging. What happens is I think I have the diagram. Yeah, here. Okay, we go for the charging and recharging. Okay. So both anode and cathode materials into which and from which lithium can migrate. The process of lithium moving into anode or cathode is referred as insertion. The process of the movement of anode or intercalation, and the reverse process in which lithium moves out of anode or cathode is extraction or deintercalation. The lithium biased cell is discharging. The lithium is next is extracted from the anode and inserted into cathode while discharging process. Okay, when the cell is charging, the reverse process is happening. So lithium is mobile, Li2 plus, Li plus, Li2 plus, Li plus. So it varies. Okay, so this is how it is charging. So when you charge, the lithium goes from this to here, from cathode to anode, and when you discharge, it goes from anode to cathode. So charging and discharging mechanism. Okay, it all looks like very simple language. Like if you put it in the circuitry, say for example, if you have in the charging cycle, if you oxidize this, okay, so from here to here, and then say for example anode and the cathode, so one is oxidized and the other is reduced in the charging cycle. So you extract energy during the time. So that goes into the resistor. In the reverse discharging cycle, it is happening in the reverse. This one is reduced from A1 plus A2 plus to A1. That is where the lithium is again B plus to B2 plus. It's oxidation. So that's what is happening in the reduction cycle. Okay. Energy density. It's a map of energy density. Different types of batteries which we have seen, right? So lead acid is about 50 kilowatt or whatever it is. 50 kilowatt, nickel cadmium. This is the roadmap. So nickel metal hydride, cylindrical prismatic, and then lithium ion and lithium phosphate. So lithium phosphate is and the lithium polymer again. So this is the most highly used high energy density batteries as well.
Explosive, probably behind us, explosive.
Yeah, lithium is, if you keep it outside in the air, it is explosive. Because it's again an alkali metal, so it again catches fire easily, like sodium, right? So storage technology markets. So over 99% of total storage capacity. So why is this market is so lopsided? Why? Compressed air energy storage, 440 megawatt. Sodium sulfur battery, lithium acids battery, nickel, lithium ion is coming up, and then redox battery. So why this market share is so lopsided?
Water is cheap.
Huh?
Water is very cheap.
Water is very cheap. Any other?
The sodium sulfur battery, you've got to keep it hot to get it going. So you've got to supply energy to it when it isn't in use. It generates some heat in use, but you have to be sitting there. And nickel cadmium electrons, if you say lead, it's got lots of problems for us. Lithium, about half the world's lithium is in Bolivia and Ecuador. So there's a function of that moving over, especially with basketball.
Very true.
Redox flow is things like gravity, again, heavy metals and
Very well said.
compressed air.
Compressed air, it could be okay.
steel from here at night to make them very cheap.
So take out all the coal mines and put compressed air mines. So okay, so that is why my market is upset.
I don't think we use coal mines.
Huh?
I don't think we use coal mines.
You could use it to take out all the coals.
Yeah, but they don't take out all the coal.
No, I'm just joking. Yeah, I'm just joking. We take out all the coals and use it. Okay. So the capital cost comparison. So the capital cost, as you can see that its whole range is happening here between the dollar kilowatt hour with respect to the kilowatt hour. So the battery applications and the battery management with respect to the UPS power quality supplies, both different compressed air, pumped hydro. It's again the guys of the lithium ion for long duration flywheels, zinc oxide batteries. So the batteries is going to play a huge role in compare compressed airs or other batteries. So storage is eventually mostly now dependent on batteries. And similarly, the costs, capital costs involved in the different types of storage from zinc air, lead acid to up to the pumped hydro. So energy storage value and propositions. Value proposition is driven by one or more combined aggregated applications, attractive financial returns and benefits. Value proposition examples: electric energy time shifts plus TD upgrade deferral, time of use energy cost management plus demand charge management, renewable energy time shift plus electrical energy charge shift, renewable energy time shift plus electric energy time shift plus electric supply, reserve capacity, transportation, upgrade electrical service, storage to serve small air conditioning loads, distributed storage, and a distributed storage for bilateral contracts with wind generation. So there are quite a few propositions of that which you should consider. And finally, you know what it is. That's it, guys. So it's a standard home. Currently, the energy bill is about $4,500 per year. Can we make it this? Biomass, renewable energy, $900 per year. Sorry? Passive heating. Yeah. Can we make it? Finally, time for some crazy ideas. What can I put here? That's it. I use solar, I use wind, I use biomass here, I use the circuits, I use the grids, store for the house. So I don't need any government policies here, I can do it on my own. That's what I want to convey the message. Probably at the end of the class you may be thinking something like that. Yeah. Alright, that's the end of the class today. And any